Yes, hello everybody. We have today Isabella Prandoni from the INAF from Italy, Bologna. So she's going to give us today talk about radio continuum surveys with the MIRCAF and SKA. So you can start now.
Okay. Hello, everybody. First of all, thanks for inviting me to give this talk. Today, I will present some of the ongoing work, which involves my group, which is based mainly on deep surveys with SKA precursors, and in particular, I will focus on MIRCAT and LOFAR. And of course, given my expertise and field of research, this will be on galaxy AGN coevolution. I will switch off my camera now because I'm not sure about the stability of the connection. Hope you don't mind. All right, so here is the outline. Please.
Yes. So yeah, sorry. Sorry for interruption. Before we continue, we may have an issue with the Zoom in which the meeting will be stopped because of the 4 minutes limit. I'm not sure if that will happen, but if that happens, please everybody log in back again after if it does happen. So please continue.
Okay. All right. So here is the outline of the talk. I will first outline the role that radio surveys can play in the context of galaxy and AGN evolution. I will then present some of the latest results from LOFAR and MIRCAT deep fields, which are indeed providing unprecedented observational constraints to galaxy evolution models and on the role that AGN feedback can play in it. And then if I have time, we'll see, I would like to conclude by illustrating the benefits of a multi-wavelength approach in this kind of studies. So, and I will possibly illustrate some particular examples of synergistic use of radio surveys and other facilities. All right, so why are we interested in studying galaxies and AGNs in the radio band? Well, this is quite obvious, I guess, for this audience. Indeed, the radio band allows us to get information and study unique aspects which are important for galaxy and AGN evolution. In particular, as we all know, only the radio surveys can probe the jetted AGN population, which escape selection at other wavelengths. In addition, the radio band is not affected by dust extinction and gas obscuration effects, and so can provide a complete and unbiased view of both star formation and AGN populations, especially at high redshifts where such populations are thought to be heavily obscured. In addition, and especially with these new facilities which have come online, like MIRCAT, for example, radio surveys can provide a unique role in proving H1 properties of galaxies and AGN beyond the local universe. Of course, in all this, there is an important aspect, which is sensitivity. Traditionally, traditional radio surveys were really able to probe only radio loud AGNs and only the brightest star-forming systems like starburst, while now with precursors, as illustrated here in the bottom plot, we are getting to a flux regime, a sub-Milijansky flux regime, where star-forming galaxies are starting actually to dominate the radio sky, and we can also probe the faintest and luminosity end of radio AGNs. And this is particularly important because current surveys allow us to really push our studies of star-forming galaxies to cosmic noon and beyond, as illustrated in the right plot here, where you see that precursors like from LOFAR and Meerkat are really probing the range of redshift between 1 and 3, and actually deep surveys with such telescopes are designed in such a way that the detection of this kind of population is optimized. In addition, with the depth that we can reach now, we are starting to detect in the radio domain also these so-called radio-quiet AGNs, so radio AGNs which are not associated to the classical radio galaxies and radio loud quasars with big large-scale jetted structures, but rather we can detect AGNs which show a very little level of radio emission and which are usually selected at other wavelengths based on signature in the optical, infrared, or X-ray band. So these are typically radiative or efficiently radiating AGNs, which are a kind of different population from jetted AGNs, where the energy comes out mainly through the radio jet. But the fact that now we can detect them in the radio domain allows us to have really a complete picture of the AGN's populations, not only the radio loud, but also the radio quiet. And as I already anticipated, with Meerkat in particular and other precursors as well, we can really start probing H1 beyond the local universe. And through stacking techniques, for example, we can already reach redshift of the order of 1, which will be the domain which will be probed in more detail by the SKA in future. Okay, so what are some of the scientific topics that we can attack with such surveys? Well, first of all, we can certainly try to better understand the role of AGN feedback in galaxy evolution. There are several evidences that AGN play a role in quenching star formation at some point in star-forming galaxies, and then later to also maintain passive galaxies, red and dead, as we say. So to limit and to maintain the level of star formation in these objects, which remain quite passive. And this allows this object to not grow too much in mass, but remain limited in mass as observed in luminosity function. So AGN feedback is thought to play an important role in regulating star formation, both in the local universe, in particular in massive passive galaxies, but also at higher redshifts in star-forming galaxies that at some point need to be quenched and become passive. However, the details on this are not clear yet, but indeed, radio AGNs, at least, are thought to play an important role in the local universe. We see that radio AGNs are often associated with massive galaxies in clusters, and we observed a clear signature of feedback from these radio jets in the intergalactic medium. So the point is how these work at higher redshift. And is there any role of jetted AGNs in regulating galaxy evolution going to higher redshifts? Another aspect which one can think of attack with the deep radio surveys is the study of the physics of AGN radio emission. The fact that we can detect both radio loud and radio quiet AGN population means that we can get homogeneous samples from that we can use to study radio duty cycles, feedback physics. We can study the motivations behind the observed radio quiet, radio loud bimodality. We can confirm it or not, and even try to understand what is actually the origin, the very origin of this radio emission in radio quiet AGNs. Radio quiet AGNs are typically associated to Seyfert galaxies which usually are star forming. So we may think, we know for sure actually that some of the radio emission we observe in these objects is associated to star formation, but in a significant fraction of these sources, at the moment we think of the order of 30% or so, we also see a radio emission in excess to what is expected from pure star formation. And it is not clear what is the origin of this excess radio emission. We think, however, that this is linked to the nuclear activity, of course, the AGN activity. There are several mechanisms which are invoked. It can be small-scale jets, which we do not observe because we cannot resolve the source. They can be synchrotron emission associated to shocks in outflowing line-emitting gas. It can be, again, synchrotron emission associated to the corona, which is surrounding these black holes. And with deep radio surveys, we can try to disentangle among these different mechanisms. Another important point which I would like to highlight here is that current surveys, modern radio surveys, can really be used to simultaneously address both questions which can be answered through information in the radio continuum and questions that need H1 information to be addressed. And this is thanks to the fact that current radio telescopes have a much better capability in terms of correlators than in the past. And so we can preserve in a single observation both the wide band, which is needed to get sensitive radio continuum surveys, and the tiny spectral resolution, which is needed to get H1 information. And this means that with a single survey, we can trace two main outputs of galaxies. On one side, the radio continuum emission, which is a tracer of star formation or jetted AGN activity, and H1 gas contact in the host galaxies. And this is particularly important for galaxy formation and evolution studies, where all the various constituents of galaxies need to be studied to get a full picture of of how galaxies form and assemble and how they evolve. And indeed, radio surveys can provide information on two of the main four constituents, as I said, star formation through radio continuum and atomic gas through H1, while, for example, optical surveys are usually used to probe stellar masses in galaxies, and ALMA, for example, is used to probe the molecular gas. The fact that we can get simultaneous information on both radio continuum and H1 line emission is also important, more in general, to study in detail the baryon cycle in galaxies. As we know, the baryon cycle involves H1 accretion, which then is transformed in molecular gas inside galaxies, and in the densest core of densest clouds of molecular gas, we get star formation. So to be able to follow all these phases in the process, we need information on both H1 and star formation, which can be probed both by radio surveys, as I said. And again, similarly, when we want to study in detail the AGN fueling feedback process and its link with radio AGN duty cycle, we need, of course, information on H1, molecular gas again, and which is associated both to the fueling and the feedback through inflows and outflows, but also information on radio continuum, which allow us to probe the presence of a young radio jets or something like that. So in summary, what I want to say with this is that SKA and its precursors are playing a big role in this kind of studies, providing both information in the radio continuum for jetted AGNs and star formation, and in the H1 for the atomic gas, but cannot really work in isolation. And probably a panchromatic approach is important, and synergies with other facilities need to be explored and exploited, actually. And in the end of this talk, if I have time, I will illustrate a couple of examples focusing on ALMA and Euclid. All right, so let's go to the second part of the talk, where I will illustrate some of the latest results that we are obtaining with LOFAR and Meerkat. I will start with LOFAR, which is maybe less known by this audience, so it might be interesting to know what's happening there. The main survey for galaxy and AGN evolution studies, which is currently ongoing, LOFAR is the so-called LOFAR 2-meter sky survey, LOTS, which comprises two parts. One is an all-sky survey at 150 megahertz, which with a uniform sensitivity of 100 microjansky per beam at 6 RSEC resolution. And then there is a number of extra-galactic fields or regions which are well known, which are observed deeper. And actually, in these particular regions, we aim to get to confusion limit with LOFAR. So the 4 fields that we are observing are ELICE N1, Lockman Hall, Budis, and the Euclid field north. And over these 4 fields, we have spent 1,500 hours of telescope to reach an RMS of the order of 10-15 microjansky per beam. In the plot on the bottom left, you see LOTS, which comprises several steps, but as you can see, The low-far deep fields have a depth which is similar to the one which has been obtained on Cosmos with JVLA at 3 gigahertz, but lots fields altogether cover a factor of 10 larger area. So it is really state of the art at the moment. In addition to these products, we also we are actually starting to exploit the international baseline of LOFAR. As you know, LOFAR has most of its antennas in the Netherlands, which means on a scale of 100 kilometers, which means a resolution of 6 arcsec at 150 megahertz, but there are other stations in Europe, all around Europe, and so exploiting these baselines, we can get down to 0.3 arcsec resolution, which is really unprecedented at these frequencies. So where we are now, the first data release of LOTS Deep regards 3 fields, the Lockman Hole Budes and the Lysen 1, for a total of 25 square degrees, and to a noise, a sensitivity of the order of 20 microjansky per beam. But we are already producing full depth images. In particular, we have obtained a full depth image for Lysen 1, combining together 500 hours of observations, and we get down to 11 microjansky per beam RMS, which is what we expect for this observing time. So we go down a factor of 2 with respect to the data release 1. These full depth data sets are not released yet. There is only an internal release. So most of the results that I will show are actually based on the first data release data products. As I said, we are also trying to include the international baselines in the data reduction to improve the resolution. This is very computing expensive, so we are proceeding quite slow. But here is already a result that we obtained a couple of years ago from 8 hours of observations on the Lockman Hole, where you can see the beautiful morphologies that pop up when we exploit the international baselines. So some of the most exciting results that we are obtaining with low-far deep fields. Here I illustrate the reconstruction of the star formation rate density as a function of redshift that we obtained by combining the 3 fields released with DR1 on the right. The main point here is to try to get a star formation rate density determination which is unbiased, so it is not affected by dust and gas obscuration effects, and this can be done in the radio domain, as I said. And as you can see, the black points, which are those in our work, tend to remain above the dashed black line, which is the determination, the reference determination by Maddow and Dickinson in 2014. So as you can see, at least on the redshift probe so far, between 1 and 3, the radio selection allows to recover more star formation rate density than is done at shorter wavelengths. Another analysis, statistical analysis, regards radio AGNs. So we are trying to constrain the role of jet-induced feedback at high redshift and the lower stellar masses. As I said before, we know already that jet-induced feedback has a role in massive and passive galaxies in the local universe. What is not clear if it has a role also in less massive galaxies and at higher redshifts. So as far as redshift is concerned, the left panels show our determination from the Loeffler deep fields. We show that the AGN kinetic power remains constant over redshift, while the kinetic power associated to passive galaxies, which is the red curve, goes down at redshift larger than 1. So this means that probably passive galaxies, the AGN feedback, it is important at low redshift in the local universe for massive passive galaxies, but at higher redshift, these kind of sources probably become less important in this respect, but another population of galaxies start to host jetted AGNs and keep the AGN kinetic power density flat. So probably in the high redshift universe, it is this jet-induced AGN feedback is not associated to massive and passive galaxies, but rather to star-forming galaxies. And from the panel on the right, we show another study, which is again based on Loeffler, LOTS survey, but not the deep fields, but a wide survey, which show a study of jetted AGNs in the nearby universe. And from this plot, you can see the different curves correspond to different stellar masses of the host galaxy, of the AGN host galaxy. And as you can see, it is confirmed that massive galaxies, which are the darker lines, tend to be more often the host of a radio AGN. So the fraction of radio AGNs in these galaxies is very high, of the order of 90 or 100%, while at lower stellar masses, these fractions tend to decrease. But if you have radio surveys which are sensitive enough to probe lower and lower radioluminosities, as it is the case of Loeffler, you see that the fraction of radio AGNs tend to increase, going to lower luminosities, and finally get to very high fraction of the order, again, of 90, 100%. So it seems that provided that you can go at lower, you can probe lower luminosity systems, such radio AGNs seem to be ubiquitous. We are also using the LOTS deep fields to constrain radio source evolutionary models and to update the existing SKA simulated catalogs like T-Rex, for example. And here is a work done by a PhD student, a former PhD student, working in Leiden at the time. So what we found is that when we compare the various source population as probed by the LOTS deep fields, which are the various points shown in this plot, with T-Rex simulated catalogs, we see two regions where there is a significant discrepancy. At sub-millijansky fluxes, we see an excess of star-forming galaxies and also radio AGNs with respect to simulations, while at millijansky fluxes, we see a deficiency of both star-forming galaxies and radio AGNs with respect to the simulation. We investigated these discrepancies a little bit further, in particular with the help of spectral index analysis in the Lockman Hole, where we have both a deep 1.4 gigahertz survey and the LOFAR 150 megahertz survey. And we found that this discrepancy can be ascribed to a discrepancy between the spectral index of the simulated galaxies and the spectral index that we observe. In particular, the excess of star-forming galaxies, some Milijansky fluxes, is probably due to low redshift star-forming galaxies, for which simulations predict a flatter spectral index than observed. While the deficiency of radio AGNs at Milijansky fluxes that we observe is probably due to misclassification of radio loud AGNs, which appear to be radio loud at 1.4 gigahertz, but appear to be radio quiet at 150 megahertz. And this is due to the fact that going to lower frequency, the radio emission is more and more dominated by star formation processes rather than AGN processes. And this is clear here because you see that these kind of sources have a flat spectrum. So there is a flat spectrum AGN core which dominates at higher frequencies and is swamped by the star formation radio emission at lower frequencies. So we use this constraint to update the latest version of the T-Rex catalog, as discussed in Bonaldi et al. 2023, but we also use these constraints to try to develop new models, possibly not based on empirical observations, but rather physically motivated. And here I'm showing an ongoing work by my postdoc Giulia Marchetti, Marica Giulietti, who is actually developing a new model based on recent near-infrared redshift-dependent galaxy stellar mass functions. And with this model, we are not only able to reproduce the luminosity function observed in the LOTS deep fields, but we also find a better agreement with the presence of a significant population of massive galaxies at high redshift, which have been recently observed by JWST. Going to MeerKAT, I will focus on MIGHTY, which is certainly the state of the art for what concern galaxy and AGN evolutionary studies. As you probably all know, MIGHTY comprises 4 fields: Cosmos, XMM, LSS, extended Chandra Deep Field South, and the LICE South. This is a case where where we can provide both radio continuum and H1 data products, as I illustrated before. And here is the current status, updated a few months ago. As you can see, Cosmos has been full, and XMM, LSS have been fully observed. The Chandra Deep Field South is partially observed, and ELISIS 1 is still missing. The results I will show in the next slide are based on early science data from MIGHTY. So this is 25-hour observation focused on Cosmos. and the sensitivity in the radio continuum is of the order of 5 microjansky per beam. It is confusion limited. While in H1, we have a sensitivity of the order of 80, 130 microjansky per beam, depending on the frequency. So one work my group has been involved in is shown here. Alessandro Bianchetti, who is a PhD student at the University of Padova, is studying, he's exploiting stacking, H1 stacking, to get H1 stellar mass scaling relations at redshift 0.4. His results are shown in the two panels on the left, in comparison with other determination at lower and higher redshifts. The lower redshift is from Guo et al. 2021, and the higher redshift Z equal 1 comes from GMRT by Choudhury et al. 2022. As you can see, by comparing these three curves, we see that the shape of the relation, the H1 stellar mass relation, seems to be invariant with mass, so it doesn't seem to change, at least at first order, and has a slope of the order of 2, which is less than the slope observed when we study the scaling relation between molecular gas or star formation rate and the stellar mass, which is of the order of 3.5, 3.6. So it seems that the H1 has a less prominent dependence on stellar mass. It is also possible that these points can be fit by a two power law function, as shown on the right, the red curves, but this needs to be confirmed on a larger statistical basis. Again, using the COSMOS early science MIT data, we are trying to start exploring the H1 dependence on environment. And as you can see in this other work by Sinigaglia et al., there seems to be a environment-dependent content of H1 in galaxies. This is perhaps expected with galaxies in the densest environment showing less H1 content, so being H1 deficient, and which is something which is sort of expected, I would say. So how much time do I have? If I can proceed further,
Yes, if we don't get caught by Zoom, we can do 15 minutes more.
All right, okay, so I will pass to the last part of the talk, which is about synergies. So as I said at the beginning, it is important to complement radio surveys with multi-wavelength information, particularly multiband imaging or optical near-infrared spectroscopy, and this is important to get very basic information about radio sources. Radio emission alone does not tell us much about the properties of the sources that we are observing. We need to identify such sources, so find the host galaxy, find its redshift to get luminosities and other important physical properties, and And this can only be done by complementing the radio surveys with information at other bands or spectroscopy. And this is, for example, illustrated here in these two plots, which show how ESO telescopes and in particular spectrometers mounted at ESO telescopes can help SKA-related surveys to provide, to fully unlock their scientific potential. For example, for galaxies, you see on the left that an instrument like MOONS, which is the yellow lines, can provide counterparts and identifications for almost all galaxies on all range of star formation rates up to redshift 2 or more. On the other hand, for radio AGNs, again, an instrument like MOONS, so a synergistic use of radio surveys and ESO spectroscopy surveys can provide, again, counterparts and information on the host galaxy for radio AGNs up to redshift 3 or more. But this is very basic information, and this is also one of the motivations, or maybe the main motivation why we study very well-known extragalactic fields, where all this complementary information is already available. However, a synergistic approach among different facilities is also important for detailed studies of single objects, where we want to study, we want to get a full picture of the various components which are important in these galaxies or AGNs, but also to get information on the wider cosmological context in which the process that we are studying happen, and particularly, for example, the environment in which this happens. And in the following, I will provide one example of the first kind of studies, and then I will I will say something more on the role that Euclid can play to help radio surveys to get information on the wider cosmological context. As far as resolved multi-component studies are concerned, I will show some results, some latest results, which involved MeerKAT. For studies to study low local radio galaxies, so very nearby objects, and to try to understand the AGN fueling and feedback cycle in these objects in very much detail. In particular, I will show here the results for one of such radio galaxies, which is NGC 3100, which is hosted by a small group, is actually the central galaxy of a small group. And this has been followed up at various wavelengths with VLA first, then ALMA, ESO, integral field units, HST. And here are shown some results. As you can see, there is a small scale radio jet in this source, which is the black contours in these panels, which is 2 kiloparsec long. So it's quite young. It's not a super young, but it's quite young radio galaxy. And the colored emission is the SKAO observed with ALMA. As you can see, there is a rotating disk on a same scale, so again a couple of kiloparsec. And as you can see on the right, in the two panels on the right, this CO disk is disrupted at the center due to the passage of the radio jets, which remove or excite the gas, which is not observed in the molecular phase anymore. So this is a clear example of a jet-induced feedback in action, which you can appreciate combining radio continuum and ALMA observations. But what you also learn from this observation is that even in the case of these passive galaxies, which are the host of radio galaxies in the local universe, there is a significant amount of molecular gas at the center, which may be an essential link to the fueling of the radio of the AGN and to the production of the radio jets. And actually these CO disks, like this one, have been observed in several other local galaxies, radio galaxies like this one, as we actually observed a statistical sample, but even if I'm showing only one case. One question which arises from this observation is, what is the origin of this gas? Particular if it is of external origin, and this can be addressed with H1 observations. And indeed, we followed up these and other sources in this in our sample with the compact array first and then Meerkat to get information on the H1 environment. And the results are shown here. On the left, you can see that our galaxy is not detected in emission in H1, is only detected in absorption, as shown in the panel in the last panel on the right. But if you focus on the panel on the left, you see that several galaxies in this group are H1 detected, and in particular a galaxy to the north, from which you see a clear tail of gas or stream of gas getting down to our radio galaxy on the south. So this is a clear evidence that the gas is of external origin, coming from strip gas from a companion galaxy. Another interesting result from this study is shown on the right. The fact that we observe the NGC 3100 in absorption tell us a couple of things. First, that we see an H1 disk, I mean the broad absorption line that you see on the right panel is associated, can be modeled by a disk. And in particular, we could model it with a disk with the same parameters as the CO disk that we observed in this galaxy. So this means that CO and H1 are co-rotating in the nucleus of this galaxy. So the H1 that comes from the external environment settled down in a disk like the CO at the center, from which the AGN gets fueled, as shown by the narrow absorption line on the right, which indicates fueling, so an inflow, an H1 inflow toward the nucleus. And actually, this inflow is, which has a double peak, as you can see, is associated to a double peak emission in CO, which is shown on the in the plot on the top right, and circled by the red circle to highlight it. And these two features, the in CO and H1, are clearly associated, and both associated to an inflow in toward the central black hole. And indeed, this feature that you see in CO cannot be modeled by a disk as the rest of the emission. Passing to our last example. Are you still there?
Yes, we are still here.
Okay, no, because perhaps the 40 minutes have passed. So the last example that I want to make is about Euclid. You may be aware that the Euclid satellite has been launched last year. It will perform a wide survey, 14K square degrees, in both the northern and southern hemisphere, and will also observe to a 1 magnitude deeper level 3 deep fields, so-called deep fields, Euclid deep fields. And the main aim of Euclid is, Euclid is a cosmology experiment, but to do its cosmology science, it will exploit both weak lensing and spectroscopy to reconstruct the large-scale structure at cosmic noon through spectroscopy, and also the dark matter halo distributions through weak lensing across redshift. And so an experiment like Euclid will allow us to get information about the wider cosmological context in which galaxy formation and evolution happen, and in particular to connect the galaxy properties to their dark matter halo properties, and study the dependence of the various processes on dark matter halo properties and on environment. And this is a very important point, because environment is claimed to play an important role both in AGN feedback processes, but also in the galaxy assembly phase at high redshifts. So Euclid deep fields, Euclid in general and Euclid deep fields in particular, are becoming strategic fields for galaxy formation and evolution studies, and several facilities are targeting these fields to be able to provide a full information at a wide range of wavelengths, including radio telescopes. So here are listed the 3 fields. We have a northern field in the northern sky, the so-called Euclid field north, which is 20 square degree wide. And then we have 2 southern fields, Euclid deep field Fornax, which partially overlaps with the Chandra deep field south, so it is at least partially observed by the MIGHTY survey, and the Euclid deep field south, which is 23 square degrees, which is at minus 48 degree in declination. So both Loeffler and Meerkat are observing these fields. For what concern Loeffler, as part of the LOTS deep, we are observing the Euclid deep field north. This is something that our group is particularly involved in. And at the moment, we already have a first data release based on the first 70 hours of observations of the 400 hours in total, which are foreseen. We are also implementing the international baselines to get high resolution images of this field. And at the moment, we are working at on the optical identification and photometric redshifts. And as you can see, thanks to the very deep multiband information available, the Euclid field north radio sources are identified in up to virtually 100%. So we will get a very complete identification for these kind of sources. As far as the southern fields are concerned, as I said, fornax is observed in the context of MIGHTY, and will also be covered, even if only a small part, by LADUMA, the LADUMA survey. While the Euclid field source was missing any radio coverage, so this is something that we are doing. This is a large collaboration which I'm leading. We obtained already more than 100 hours of time for a pilot survey of the full region, which is a mosaic of 134 pointings. With these pilot observations, we expect to go down to 6 microjansky per beam RMS over the full region of 23 square degrees. And as you can see from some preliminary results that we have obtained so far, we indeed reach a median RMS of the order of 6 arsec, even after just a preliminary data reduction. We will probably do even better when we will have finalized our data reduction pipeline. As I said, these Euclid fields are strategic for the future, and so they are planned to be observed also by future facilities. The Euclid field south has been included in 2 of the proposed MeerKAT Plus surveys. The one which will cover the full southern sky at S-band by Rancho et al., and also the L-band survey proposed by Joshua et al. As far as the LOFAR, the northern deep field is concerned, there is a plan to observe it with LOFAR 2.0, which is an upgrade of LOFAR, which is coming online soon. There is a survey proposed for LOFAR 2.0, which is called the LUDO, and as part of this survey, we intend to observe a sub-region of this field of the order of 3.54 square degrees at full LOFAR resolution, so down to 0.3 arsec, down to 2 microjansky per beam RMS. And as you can see on the plot on the left, LUDO will be probably the first SKA-like survey, which will have the sensitivity that we expect from SKA surveys. Well, this is all I wanted to tell you. Probably it is even, it's a lot, but anyway. So I let you with my take-home messages, and I just wanna finish by thanking all the young PhD and postdoc collaborators that I have and that made possible to obtain most of the results that I've shown. Thank you.
Okay, thanks, Isabella. So for the talk, very interesting. So we can have maybe a couple of quick questions if there's any. Yes, Stabili, please go ahead.
Okay. Hello, Isabella. Thank you very much for that comprehensive talk. Low-pass
I cannot hear very well. Can you?
Okay. Can you hear me now?
Yes.
How's that? Okay, good. All right. I was saying, thank you very much, Isabella, for that very comprehensive talk and overview of current say results and future observations with Euclid. So my question firstly is about the Bondi et al. Your collaborator Bondi's work with the spectral index, let's say simulations versus observations. When you say 32% of the, when you say low radioluminosity sources, if I remember correctly, are misclassified as radio loud AGN due to the spectral index.
Yeah.
The K correction essentially associated with sources with flatter spectral indices. Is that so? I wanted to ask you, is the classification of radio loud AGN in this case based on
It's based on radio excess.
Radio excess. Okay.
Yeah.
All right.
So in lots, the radio AGNs are identified based on an estimate of the star formation rate from an independent estimate of star formation rate from set fitting. And then a comparison between this value that we estimate and the radioluminosity that we measure in this source. So if we observe an excess radioluminosity with respect to the one that we expect for that given measure or estimated star formation rate, a significant excess, I would say, 2 sigma or more, then we classify this object as radio loud.
Radio loud. Okay.
Yeah. So that means that if there is an AGN-related emission, but the source does not satisfy a 3 sigma excess threshold, but is just below, it will be identified as a radio-quiet AGNs or a star-forming galaxy. And this means that, for example, if we do the same exercise as we did in the Lockman hole, based on a 1.4 gigahertz emission, if we have a flat spectrum source at 1.4 gig, a flat spectrum AGN in this source, at 1.4 gigahertz, probably the radio emission from the AGN is more relevant with respect to the radio emission in the same source from star formation. So it has a larger relevance. It is more prominent, I would say.
Yes.
It is easier for this source to pass the 3 sigma threshold of the radio excess.
Yeah.
At lower frequency, at 150 megahertz, where due to the fact that synchrotron emission goes up, I mean, it is, especially if associated to star formation, is steep, no? The emission. So at lower frequency, you see a lot of emission associated to star formation. But if the radio emission from the AGN remains low because the spectrum is flat, the prominence of this AGN-related emission with respect to the emission associated to star is less. And so it is easier for this object to fail the 3 sigma threshold for radio loud definition. So the fact that we see this in a 30% of objects means that these objects probably host a flat radio spectrum, and indeed we measure a flat radio spectrum. So, yeah, this is something that, of course, models neglect because it's too detailed, but may result in wrong reproduction of source counts.
Okay. And with regards to, you can say, solving this particular problem, especially for wide statistical samples that you obtain from deep surveys, is there a way forward? Is someone working on that in your group?
What we did as in the first place was to inform the people who are responsible for the T-Rex simulation, so Anna Bonaldi, about that, and she tried to statistically reproduce this effect by including the possibility to have a flatter spectrum for low luminosity AGNs in their model. As far as we are concerned, we are trying to follow another approach, as I very briefly said at some point. We are trying to start from a physically motivated model. For the moment, we are actually limiting our work to star-forming galaxies, so trying to reproduce the correct number density of star-forming galaxies, so avoid an excess of star-forming galaxies, which may be due to misclassification. So the idea is to start from physical laws, like, for example, mass functions, stellar mass functions, and particularly the latest determination of them. Actually, we did something similar in a previous work by Mancuso et al. 2017. We are now, which is however not reproducing very well the latest observational constraints from the latest deep radio surveys. So we are now updating this model, so starting from more recent stellar mass function constraints, and then applying the latest determinations in terms of relations between star formation rate and radioluminosity, which has been found recently to be dependent on perhaps not only or not particularly on redshift, but more on stellar mass. You may be aware of the works by Smith et al. Based on Loeffler deep fields, or by Del Vecchio et al. Based on IT. Found a dependence of this star formation rate radioluminosity relation on stellar mass. So we implemented this. And then, we also implement, to get the star formation rates from the stellar mass function, we implemented the latest determination of the main sequence relations, so stellar mass star formation rate relations. And actually we found quite a better agreement. So our idea is to start from there, and rather than from observed luminosity functions, and try to reproduce the observed luminosity functions.
Okay, I see. All right, thank you very much for the detailed answer.
Thank you.
Okay, thanks, Stabile, for the question. And yes, I think we are over time, but hopefully we didn't have any problems with the Zoom. So thank you again, Isabella, for the talk, and everybody that participated today. So see you in the next seminar. So thank you very much. Bye.